Let's consider another function that might be in a security-sensitive part of your application, which is the modular exponentiation step of RSA decryption. Remember that modular exponentiation happens because we can't really take x to a private key power and then perform a modulo after that, because a private key is on the order of 2,000 bits, and so the exponentiation of that would have to be on the order of 2 to the 2,000 bits, which is more than the number of atoms in the universe. Modular exponentiation works by squaring until we get up to the right number, but at each step after squaring, then we do a modulo at that point. So it's a combination of squaring and multiplication as we go. So the loop looks like this. We go from the top bits down. We are going to take the result that we have currently, square it, and take the modulo. And then if the bit that we are looking at is set, then we will multiply the accumulated value by x one more time, and then do a modulo. The number of times that this loop runs is always going to be the same, because it's based on the number of bits that we're using for a key. So that is a good feature of this loop. But you also see that there is an if conditional in this loop. And so, based on timing, we might be able to tell whether this if branch is taken or not. Every time there is a bit set in the private key, right, something not supplied by the user, but something that we wanted to keep private, every time there is a bit set, then we are going to do this extra work, an extra multiplication, and keep in mind that these are big integer multiplication, not just regular integer multiplication, so they do take a significant amount of time. Overall, then, the time that's going to be taken by this for loop depends on the number of bits that are set in the private key. Exposing the number of bits is maybe bad, but also not terrible, because if we picked a random number up to key bits long, then probably half of those bits are going to be set and half of them are unset anyway. So that's not so much the problem, at least if the only thing we get to observe is the overall time taken by the for loop. But if we're able to watch this program as it's running, we may discover that the hard work that we're doing here to do this extra multiplication every time the bit's set, it can be reflected in not just the time it takes, but the power used by the processor to perform that multiplication and division every time a bit is set. And so that means the power usage of the CPU might look something like this. When there's a 1-bit set for an iteration of the loop, it uses a lot more power, and when there's a 0-bit set, then it uses less power. The problem here now is that we're not only exposing how many 1s and 0s there are, but in what order we have 1s and 0s. In fact, you could just read off the bits of the private key by distinguishing the long 1 pulses here from the short 0 pulses. This detection of a private key by power consumption turns out to be entirely practical. In a paper from 2014, the authors set up a laptop to run an RSA decrypt step, and they connected themselves to this analyzer here by not having the laptop plugged in, but touching the power outlets where the laptop would otherwise be charged, and watching the variation of power draw on that line. And by watching the variation, they can turn these into 1s and 0s and directly read off the private key that laptop was using for the RSA decrypt step. They didn't even need to connect to the power outlet here. It turns out they were able to get the same information by just grabbing the screen of the laptop. There was enough about the power system being communicated just through the screen that they were able to get the same data out. Or even by not touching the screen, not working by a conductor through their arm, but by just measuring the change in electromagnetic fields through nearby the laptop. In fact, they were able to get that information not by electromagnetic waves only, but even by sound. It turns out that CPUs make different sounds based on the instructions that they are running. And so here, it's not just about power consumption with RSA, but about observing what sequence of instructions are being run, not just how much power those instructions use. And they were able to, without touching a machine, just having some microphones in the same room, be able to infer something about the instructions that were being run by a computer as it was doing its work.